Good afternoon. We are Group 4. Group members contains Wang, Cheng-Zhong, Lin, Hao-Lun and Li Yi-hung. Here is the outline today. Please take a look. Starting from the introduction. According to the data from the government, the top cause of death in Taiwan is cancer. And lung cancer has been the leading cause of cancer-related deaths for years. Especially in East Asia, among types of lung cancer, the most common is the lung adenocarcinoma. Several techniques have been proposed to the diagnosis of LUAD, such as low-dose computed tomography scan, magnetic resonance imaging scan, and needle biopsy, etc. Fortunately, in recent years, one of an important pathologic characteristics observed in needle biopsy called tumor spread through airspaces was described. To speak of our target problems. In practice, reviewing all images of biopsy by solely humans' eyes costs a lot of time and efforts. To improving the efficiency of physicians' sensitivity for lung adenocarcinoma detection, an advanced AI-based method must be developed to support the diagnosis of lung adenocarcinoma. To take a deeper look into the field of artificial intelligence, model development has always been one of the toughest aspects to explore, so we can further refine our problem to what is an advanced deep learning-based model for the field of detection on spread through airspaces, STAS, utilizing images of lung adenocarcinoma biopsy? In this report, the work is to do object detections. Dataset we used is the LUAD pathological section image data provided by T-Brain AI Cup 2022 competition. Basically, spread through airspaces refers to the spread of tumor cells from the edge of the tumor along the alveolar cavity to adjacent normal lung tissue. Tumor airway spread has a significant impact on the risk of recurrence in patients with lung adenocarcinoma after surgery, and it has become a routine item for pathological examination of LUAD. Here we want to share the SSD network we used first. Although the past faster RCNN has not bad accuracy, it has the problem of excessive calculation. In order to solve this problem, SSD readjusted the pipeline of the model. The basic architecture of the feature extraction network is to use VGG16, remove some fully connected layers, and add some convolutional layers. It also uses dilated convolution to make up for the receptive field which is lost. SSD abandons the proposal stage in previous network and uses the mechanism of anchor. Anchor is a predefined box with a fixed position and size. We can understand it as that proposal stage is set in advance and fixed. To sum up, SSD uses convolutional layers of different depths to predict different size targets. Here we have a brief introduction for YOLO model we used. Basically YOLO is composed of 3 items. The first one is backbone network for feature extraction. Second one is neck network for feature aggregation. Last one is head network for object prediction. Compared to SSD we mentioned before, YOLO v3 is also a single regression model in predicting bounding boxes. Based on YOLO v2, it has the batch normalization, higher resolution and anchor boxes as well. In the prediction of the image, the complete end-to-end training can be realized by only a set of CNNs. It predicts multiple bounding boxes and for calculate the probability of the each object at the same time. It also uses the objectness score to each predicted bounding boxes and compose the training loss item. Moreover, YOLO v3 add connections to the backbone network to improve feature extraction. Last but not least, it makes predictions at 3 scale level, which predict each bounding box in each level and calculate the probability of them for the corresponding category. Here in YOLO v5, it is based on YOLO v3 and improving some small parts of network. First of all, the anchor boxes are not predefined, it can be trained in the network, which optimize the bounding boxes prediction very well. Moreover, it include the CSP network in the backbone stage which can alleviate gradient vanishing problem powerfully, bolster feature propagation and encourage the network to reuse feature. To make sure the stability of network, it also adds the image mosaic method to help train like the image on the right. Last but not least, it modifies the origin loss function for bounding box. The original IOU loss only focus on the 2 bounding boxes intersection ratio. But ignore the size of the object, so it cannot directly optimize those parts without overlap. Luckily, GIOU fixes this problem by taking the non-overlapping area into consideration like the formula in the right. Here is the model architecture. We can see the 3 part of models, backbone, neck and head for detection just like what we mentioned before. Last part is our performance. The experiment got the map score 84.32% in public leaderboard with YOLO v5 model. In addition, we used some testing images for the bounding boxes prediction and its corresponding confidence score shown on slides. By the observation, we can conclude that the YOLO v5 does have a great performance so far. In summary, besides that YOLO v5 has the most acceptable performance. Future works include, first, trying another SOTA models, for example, SWIN transformers. Second, development of the system, and third, we may try reinforcement learning architecture. That's all for today. Thanks.